Hey everyone, we're going to start our next unit on mechanical waves. Little change of pace for this unit. We're going to go with the PowerPoint because waves are kind of a thing that moves around a lot, and it's easier to understand with some animations in there. But it does follow right along with the notes. So if you have the notes, I tried to make it sort of match exactly up with that, so you can just kind of take notes as you go. Alright, mechanical waves. Let's get started. Our next two units are going to be about waves. This one will be about what we call mechanical waves, and our next unit will be what's called electromagnetic waves. Since we're talking about waves for about the next month or so, we should figure out what they are. A wave is anything that will transfer energy without transferring mass. So we're going to transfer energy without transferring mass. So let's think about like a way you can transfer energy. So one way that you could transfer energy while moving mass would be like, let's say you throw a baseball somewhere. It's in your hand, and as you throw it, it's moving, so it has kinetic energy. And then when you throw it, let's say you throw it far away, well, that kinetic energy moves from here to there, right? It moves with the baseball. The baseball was moving here, and then it's moving over there. So you transferred energy. You moved it from here to another place. But you also transferred mass, meaning like the baseball itself moved as well. Like the baseball has mass, and it moved from here to there. So a baseball is just an object, because when you transfer that energy, you're transferring the mass. A wave is different. We are transferring energy without transferring that mass along with it. So a nice example is this guy right here doing the jump rope, ropey thing at the gym that they have. So what he's doing, when he moves his hands up and down, he's creating a wave. And that wave is transferring energy. I think I can write on this. Yeah. Okay, so he starts his motion like over here, and then the energy moves along the rope and ends up over here, right? He starts the motion at where his hands are, and then that motion travels along the rope. So we're definitely transferring energy. But what makes it a wave is that we are not transferring mass. What I mean by that is this. Look at the rope in his hands, like the part of the rope that he's holding. Is that piece of rope, is that little bit of mass traveling down? I would say no, because it's in his hands, and then it's still in his hands, and then it's like still in his hands. Since that mass didn't move along the rope, we moved energy, but we did not transfer mass. And so that's what makes this a wave. We move energy without moving mass. This topic is about mechanical waves. Our next topic will be electromagnetic waves. So everything I talk about for this unit, it takes like 2.5, 3 weeks. Everything I talk about this unit is an example of a mechanical wave. What makes it a mechanical wave? A mechanical wave is a wave that travels using a physical medium. So basically, like a physical medium is just like, it's like physical objects that vibrate. So using physical, actual physical objects. Yeah, whatever. Physical objects. As an example, let's go back to our rope guy. There's a physical thing that's moving here, right? It's the rope. It's a thing that is moving. That's what makes this a mechanical wave. An electromagnetic wave isn't like, it's not particles or things that move. It's like a fields that go back and forth, so it's a little bit of a different thing. So they use a physical object, which is like a medium, and all mechanical waves require a medium. They need something to travel through. I've used this word a couple times here, medium. So you got to know what that means as well. So a medium is the material through which a wave travels. Whatever it is that the wave is traveling through, the word we have for that is a medium. Going back to our jump rope. Sorry, I'll go back in a second. The medium for the jump rope is the rope. That is what the wave is traveling through. That's the medium that it moves through. When you think about it like that, this statement makes a little bit more sense. All mechanical waves require a medium. So like, can you have a jump rope wave without a jump rope? No, because where would the wave be? That would be just this guy waving his hands in the air, so you wouldn't have this wave without that medium for it to travel through. Another couple sort of common examples, or some easier ones here. What's the medium for an ocean wave? So like an ocean wave, what does it travel through? Well, it travels through water. Right? Ocean waves, well, that's what the wave is moving through. When I say that this requires a medium, what I mean by that is, can you have an ocean wave without water? Well, no, because that wouldn't even make sense. For a sound wave, what does sound travel through? As I'm speaking to you now, sound is going from your computer speakers to your ears, or maybe from your headphones to your ears. What's the sound traveling through in order to do that? It's moving through air. Sound can travel through other things, like you can hear it through a door or something like that, so it can move through solids as well. But that would be the medium typically for sound. And sound requires air. If you don't have any air, you don't have any sound, because there's no medium through which it can travel. Okay. Pulse. So, what a pulse is when we talk about waves, a pulse is a single disturbance. It's like a single vibration that moves along. So it's just a single little piece. So this is, you don't have to memorize this definition, but it's a word I'm going to use a lot. Here we're looking at a couple examples of pulse. So like right here, see how we just have like a single sort of, peak moving along? We call that a crest, the top of a wave. It moves this way, and then it moves back. Here we've got a single pulse moving this way. Here, I would consider this wave thing a pulse, because see how it's just like a single wave that travels? That makes it a pulse. So a pulse is, what makes it unique is that it's a single piece of a wave, or a single disturbance that moves along the medium. The other side of that is going to be a periodic wave, which is a regularly occurring pulse. So something that's regularly occurring means it just happens, like, it repeats itself, essentially. So if the wave pool that we looked at before was a pulse, because remember that was like a single wave, then this wave pool would be a periodic wave, because see how we create one wave, and then the next wave, and then the next wave. Since it happens at regular intervals, we would say that it's a periodic wave. Our jump roper from the other page would also count as a periodic wave, because see how he doesn't just send one of these pulses down? He does it, with some frequency, with some regular occurrence. And that's what would make this a periodic wave. Alright, we're throwing a lot of vocabulary at you today. This is one of the more important ones that we're going to talk about, are transverse and then longitudinal waves. A transverse wave, the definition for this that you'll have to remember, is when a wave's velocity is perpendicular to the motion of the medium. I'm going to make a big deal out of that perpendicular idea. So a transverse wave is when the wave's velocity is perpendicular to the motion of the medium. So if you're trying to just memorize the definition for this, here's like the best thing I got for you. The mathematical symbol for perpendicular is like an upside down T. Maybe you did that in a geometry proof somewhere in one of your math classes. And that's kind of like an upside down T, right? As in, transverse. Or like a T is perpendicular. I don't know, I'm trying. So, when the wave's velocity is perpendicular to the motion of the medium. But we should probably also understand what that means. So let's look at this. This is an example of a transverse wave. Transverse waves are going to be waves that have that sort of familiar up and down, like wave-like shape to it. So for this one, we've got a wave, and let's pause for a second and think about this. Which way is the wave's velocity going? Sorry. Which way is the wave's velocity going? Is it going to the right or to the left? Take a moment, pause, and think about it. Hopefully you thought to yourself, the velocity is, oh no, moving to the right. The reason I'm saying it's to the right is I'm just going to keep my pen over the top of, the crest of one of these waves, or on the top of it. And you see how it's going to the right? That's the direction of our velocity then. Now, let's look at the motion of the medium. The medium is going to be any one of these particles. So this animation has a couple of them highlighted in red. For my students, I think you might know I'm actually colorblind, so I have a little trouble with this. I think this one's a red one right here. So what I'm going to do is I'm going to keep my pen directly over that dot, and I'm just going to follow it up and down. So I'm just going to follow it up, follow it down, and you can see my pen leaving behind the path at which, the object is going. But it looks like that red dot is just moving straight up and down. I know I drew over it, but I want you to pick a different dot and just follow its motion. And what you should notice is it just goes up and down, and up and down, and up and down. So the particles are going, again, up and down. Now, the velocity, we said, was to the right. You see this perpendicular idea that we have right here, that as the wave moves to the right, the particle moves up and down. Those are perpendicular to one another, left and right, and then up and down. That's what makes this a transverse wave, is that the motion of the particles is perpendicular to the velocity of the wave. As the velocity is side to side, the particles are up and down. Transverse wave. Shout out to El Pereira. I don't know who that is, but I stole his thing for this. Let's look at a couple examples of transverse waves. So let's start with the wave at a stadium. I'm looking at this one right over here. That's kind of a nice example of what a transverse wave means. If we look at this this one right here, we've got the wave. It looks like it's moving kind of from right to the left. I'm going to change color so that it might be more visible. Let's go with this color. Moving. Nope, that didn't help. Even worse. Alright, I'm just going to draw it up here. It looks like the wave is going from right to left. I've got it going that way. If you look at the people standing up, it kind of looks like they're going that way. Now, let's look at the motion of the individual people. If you were one of the people in the crowd, which way are you moving? Well, you're not sliding along all the rows and bashing into everyone next to you. You just stand up, and then you sit down. That's a transverse wave, kind of. See how we've got the particles, or the medium, which I guess in this case would be the fans, are moving up and down, while the wave moves from right to left. And again, what makes this transverse is that those two things are perpendicular. They form a right angle with one another. This over here on the left, I kind of like. It's a little hard to see the wave traveling across because the GIF file is just kind of fast. But I've got, if the person making the wave is over here, then I've got the wave as traveling towards the right. But what I really want to point out is, see right here, the person put a piece of tape or something, or a ribbon tied to it. And if you look at the direction that that's going, it's straight up and down. And that's what makes it a transverse wave, is that as the wave is moving to the right, the piece of tape, or that one little part of this slinky is moving directly vertically. So again, this perpendicular idea means it's transverse. It's all the waves that have that sort of, again, familiar kind of snake-like shape to them. Okay, those are transverse waves. The other type that you're going to need to know is a longitudinal wave. If a transverse wave means that the medium vibrates perpendicular to the velocity, then a longitudinal means that the medium vibrates parallel to the velocity. Okay. So that's what makes it a longitudinal wave. An example of the longitudinal wave, and probably the most common example that we're going to talk about this unit, is sound. Sound is an example of a longitudinal wave. Longitudinal waves look very different. You could probably tell just from this animation right here. Oops. Sorry. Okay, so here you're looking at an example of a longitudinal wave as it travels across the screen. Now, for this one, I would also say that this one is moving from left to right. I'm saying that because looking at these sort of compressions, I'm going to pause it so that You can kind of see what I'm talking about. See these compression areas right here, and right here, and right here? Those are what I'm looking at as they move from left to right. So let's animate it again. And you can kind of see them moving across. And I'm going to trace one, or trace alongside one, starting here. And again, I'm just following this like little squished together area as it goes to the right. So that's the direction of the wave's motion. We have this thing that's moving across. But what makes these sort of, again, very different from transverse waves is that if we follow any one of these particles, and this one also has one highlighted in red, it's right here. And if you follow the motion of that particle, which way do you notice it moving? It's not up and down anymore, it's actually side to side, moving from right to left. And if we look at that direction of the wave's motion, that was to the right, the particle is moving left and right. I would say that these are two parallel lines, like they're kind of in the same direction. And so this is an example of a longitudinal wave. Again, what you notice is it looks completely different. It still follows sort of wave ideas. You're still transferring energy without transferring mass. It's just a very different sort of geometry, I guess you could say, for this type of wave. Instead of a transverse wave where you have these top areas called crests and the bottom areas which are called troughs, what you have instead are little areas of, see where all of the medium, all of these, like you could think of them as like air molecules, are all very smushed together. Those would be areas of compression, so where it's like really smushed together. And then we have these little areas, like kind of right here, I know it's moving as I do it, that are just areas where the molecules are very expanded. The physics term for those are rarefactions, but you don't have to know too much about them. What you do have to be able to do is like understand what one is if you were to see it. Obviously, if you're writing on paper, you don't have animated things in front of you. So the way that you would draw one, and you should probably throw this in your notes next to the longitudinal waves, is we're drawing areas where it's very compressed and then far apart, then compressed and then far apart. So there's a couple ways you could do that. Sometimes you'll see like a bunch of dots close together, so we'll do a bunch of dots right here, then a bunch of dots spread apart, and then a bunch of dots really close together, and then a bunch of dots spread apart, and then a bunch of dots close together, and then a bunch of dots spread apart, and you kind of get the idea. If you're as annoyed by that as I was, something else that you could do is to represent a medium that's very squished together. Sometimes we use like vertical lines that are like close together and then far apart and then close together again. Come on. And then far apart and then close together again. So maybe you prefer that representation. So again, it's still a wave, it just has this very different look to it. It means that the medium is vibrating parallel to the direction of the wave's velocity. Let's look at a couple different sort of images of one. Hopefully you get the idea. Okay. For starters, we can use like a slinky or like a long spring to create a longitudinal wave. This one right here is exactly that. We have a person pushing the slinky this way. And you can kind of see there's this like compression, right? There's this like smushed together area of the slinky that is traveling along the slinky. So we're transferring energy, but again, we are not transferring mass, because you see those coils that are in the person's hand? Those are not moving down. It's just this like little compressed area that travels along the slinky. And what makes this a longitudinal wave is, if you look at a nice example is, this is kind of like the piece of tape that we had before. The wave's velocity is traveling this way, right? And you can kind of see, like, right, looking right here, this little piece of tape. I just drew right over it, so that wasn't helpful at all. But just like the previous video, where the person had the piece of tape on the slinky to show the direction of the medium, that's exactly what we have here. And you can kind of see that it just moves like left and right? Like moves that forward and backwards. And if I draw that up here, again, see this parallel, these two parallel directions? That's what makes this a longitudinal wave. Down here, we're also kind of showing that. If we follow one of these compressions or like smushed together areas, It travels, I think, from left to right. And for this one, we took a red dot and we placed it on one of the slinky coils. And again, if you just follow the red dot, it's moving right to left to right to left to right to left. And these parallel directions, that's what makes this a longitudinal wave. So still a wave. So transverse and longitudinal, just ways of describing how is the medium moving. As the wave moves side to side, is the medium moving up and down? Or is it moving sort of in that direction, left and right? Sort of a final nice point of comparison here. The transverse wave is, again, it has that like the medium. See, the coils of the slinky are traveling up and down. If you fix your eye on any one of the coils, so I'm going to do this one right here. It goes up and it goes down and then back to where it started. But it looks like the wave is traveling to the right. And again, those perpendicular directions makes this transverse. For this longitudinal, if you follow that compression along, it looks like it goes something like this. If you follow one of those If you follow one of those slinky coils, I'm just going to pick one. I did it again. And it looks like it just goes left to right. So you can pick a different one out with your eyeball and just follow it. And again, the fact that these are parallel directions makes this longitudinal. Okay. Now we have to do some of the math for these waves. We describe waves using, today we'll just do period and frequency, and then we'll talk about some of the linear measurements that we would do. Both of these measure the timing of the wave, but they represent slightly different things. Frequency for a wave is the number of complete wave cycles that happen in 1 second. For example, 3 waves per second. It means it happens 3 times in 1 second. We call that the frequency. We measure it in a unit of, this one's got kind of a weird unit here. Waves is unitless because it's just like a number, so there's really no unit there. And we've got like per second, so it's actually just measured in 1/seconds, or just per seconds. If you don't like that, I don't love it. Just 1/seconds is very strange. So you'll sometimes see it written in textbooks or in a college class. They might write s to the -1, which maybe you hate even more. Because remember, any exponent that's to the negative is in the denominator. The one I'm going to use almost every time, and the one most people would use, is probably a word you've seen before, hertz, which we abbreviate Hz. This is a Z. What a hertz means is how many times it happens per second. For example, 3 waves per second is 3 hertz. And if you told someone in a physics class, 3 hertz, they should understand that that means 3 times each second. So that's frequency. It's how frequently it happens per second. If you're trying to remember the simplest definition there, I would go with this one. Waves per second. It's like the nicest, simplest way of doing it. Take the waves per second, and that's it. Period. Period is the time, in seconds, it takes for 1 complete wave cycle. It's measured in, I know I kind of just said it in the definition, seconds. Period is a time period. That's where it comes from. It's the time period it takes for 1 complete wave to go by. We'll do some examples. I'm going to hope it kind of clarifies that for you. You can kind of think of it as the seconds per wave. Like if it takes like 10 seconds for a wave to go by, it's 10 seconds per each wave. Now these two things are connected by an equation. It is in the reference table, so I'm going to bring that up. We're in a new section of the reference tables today, the wave section. We're actually not starting out with that first equation. We're going to start out with the second one right here. T equals 1/f. And that's our equation for this. So again, it's in a new part of the equation, and it just relates period and frequency. So T equals 1/f. I'm sorry, I lost like half my notes when I did that. F. All right. F stands for frequency, which we measure in hertz. Capital T, well, T represents time. Capital T is meant to represent a very specific time. It's meant to oh, there they are. It's meant to represent the period, which we said we measure in seconds. So F for frequency, T for capital T for period. Now this is 1 over F, and 1 obviously is not a variable. So if you know the frequency, you can always just do 1 over frequency and solve for the period. If you know the period, you can also solve for the frequency. I'm going to do that. I'll do it in a different color. You don't have to write this part down if you don't feel like it. But I'm going to put the T over 1, and then I'm going to cross multiply here. So when you do that, you get F times T is equal to 1. And I'm going to solve for F. F is 1 over the period. And the reason this is kind of important is that it means that if you know the frequency, you can always find the period, because you do 1 over frequency is period. Or if you know the period, you can always find the frequency, because 1 over period is frequency. Where it does become confusing is that if you divide the wrong way, you sort of get the wrong thing, I guess you could say. So just be careful as you go. As a nice example, I'm going to calculate the period of this one right here. Okay, so frequency is 3 hertz. Period is 1 over frequency, right? 1 over 3 hertz is... I'm just going to actually leave it as 1/3 of a second. And I'm going to leave it that way because I think it's the easiest way to think about it. And it nicely shows that frequency and period are both measurements of timing. So what this 3 hertz means is this happens 3 times every second. Okay, so how long does it take to happen once? 1/3 of a second. Do you see how 3 of those would make up the full second? Like, you know, the first one takes 1/3 of a second, the second one is 2/3, and the third one is the whole second. It happened 3 times per second. That's frequency. So they can be confusing because, yes, they do measure kind of the same thing, but they represent sort of different sides of it. One is how many happen per second. The other is how many seconds it takes for each one. Do a couple examples together. Have you try some on your own, and then obviously I'll just go over them with you. So let's try number 2. Again, another one where I'm just trying to really highlight the difference between period and frequency, and show that they're both just about timing. A fisherman's boat floats on the water and bobs up and down with the wave. The fisherman notices that the boat goes up and down once every 4 seconds. What is the period of the waves? And I think in your note packet I gave you like a hint, and I told you that period is the time it takes for one complete wave to go by. This happens once every 4 seconds. Okay, well, so how long did it take to happen? 4 seconds. That's it. That's what period means. It's the time period it takes for each wave to go. That's an S. Oh, God. It's the time period it takes for each wave to go by. So it takes 4 seconds for each wave to go by. I gave you the period. I just didn't use that word outright. Now for frequency. All right. Well, T is 1 over F, right? Okay. We know the period is 4 seconds. I'm not going to plug in my units because I'm just having a lot of trouble writing on this computer screen today. Equals 1 over F. You may already see the answer, but I'm going to sort of walk through all the math in case you're having trouble with it at home. I'm going to put this 4 over 1 and then cross multiply. 1 times 1 is 1. 4 times F is 4F. And then I'm going to divide both sides by 4. And F is equal to 1 over 4. Great. Cool. 1 over 4 is, I'm going to put it in decimal form, because I just kind of like doing that. I get 0.25 hertz. 1 over 4 is 0.25. So what are we saying here? We're saying that for each full wave to go by, takes 4 seconds. How many waves happen per second? 0.25 of a wave, meaning like not a complete wave happens within a second. All right, let's try one more together, and then I want you to sort of try the rest on your own. All right, a physics student makes waves in a puddle by stomping her feet in the water twice per second. So, like, we're looking at it here. If you jump in a puddle, if you stomp into it, waves are going to sort of radiate, outwards from that puddle. We're going to step in the puddle twice per second. What's the frequency of the waves? Well, what is frequency? I really want you kind of like asking yourself that every time it happens. If we were in class, I'd ask you like a zillion times. What is frequency? Well, frequency is the waves per second. Waves per second. Okay. Well, we're making a wave twice per second. So I would say the frequency is 2. 2 times a second, or 2 hertz. That's what frequency means. Period. What is the period of the waves created by the student? Well, if you know frequency, you can always find period. And if you know the period, you can always find the frequency. We only have one equation for this unit, so it's easy enough. T equals 1 over F. I think we know F, right? 1 over 2. 1 over 2 hertz. 1 over 2 is point 0.5 seconds. Come on. That's a decimal right there. Just make a bunch of dots. Okay, so we got 0.5 seconds, or a half a second. Which actually makes perfect sense, because if something happens 2 times in a second, how long did it take to happen once? A half of a second. So again, both measurements of the timing, they should both kind of line up with each other. If it's a nice simple number like 2 and 1/2, then, you know, it's easy to think your way through. If it's more complicated sort of decimal type thing, then, you know, maybe it's a little harder. But, you know, think your way through at the end and see if it makes sense. Alright, what I'd like you to do now is try the rest of these questions. By that, I mean try numbers 2. Oh, sorry, we just did 2 and 3. Try numbers 4 through 11. I'm going to go over all of them in a minute, but pause the video, give all of them a shot. If you get stuck on one, jump to the next one. See what you can do. Alright, so hopefully you tried numbers 4 through 11, and we're going to go through them right now. Alright, number 4. A child notices that 4 waves arrive on the shore every 20 seconds. What is the period of the waves? Okay, so we've got, I'm just going to write this all on the side. We've got 4 waves. We've got 20 seconds. Okay, so period is, remember, how long it takes for each one individual wave to go by. So, if we had to figure that out, let's do this. Again, how long it takes. So 20 seconds for 4 waves. To figure out each individual wave, what I would do is take 20 seconds, and I would divide it. Sorry, this is divided by sign 4, and you get 5 seconds. And that's it. That's like a, you know, almost like a old, when you first learned what division means problem. It takes 5 seconds for each wave to go by. Another sort of, you know, way that if you think this is a little bit easier to think about, you can think of the period as being, it's the seconds per wave. So if you've got 20 seconds divided by 4 waves, you know, seconds per wave, 20 divided by 4 gives you 5. Frequency. There's 2 different ways you can do frequency. One is, you could do our equation that we learned. If you know period, you can always find frequency. If you know frequency, you can always find period. T is 1 over... Sorry about that. T is 1 over F. So we just found the period to be 5 seconds, and I really want to point out, capital T means period. The time it takes for 1 wave to go by. We are not using the 20 seconds. That wasn't the time it took for 1 wave to go by. I think that was 4 waves total. The period is 5 seconds for 1 wave to go by. equals 1 over f. Some cross multiplication. I'm not going to show all the work here because I just don't have the room. But you should get the frequency is 1 over 5. Or, in your calculator, I think you get 0.2. Just lose that. Let's lose that. 0.2 hertz. And there you go. Period and frequency. Another way that you could do frequency that I always find very easy to remember, because I scream frequency is waves per second at you constantly, is if we've got 4 waves in 20 seconds, what we can do is we can just divide those two. 4 waves in 20 seconds. Waves per second. That's what frequency means. 4 over 20 is 0.2 hertz. So either way, you get that same 0.2 hertz. So do whatever makes more sense to you. Either find the period first, or, again, frequency is waves per second. 4 waves in 20 seconds. Waves over seconds. Number 5. Tall buildings are designed to absorb some of the energy from high wind speeds by swaying back and forth in a controlled manner. The Willis Tower in Chicago sways back and forth with a frequency of about 0.12 hertz. What's the period of vibration? Well, if you know frequency, you can always find period. If you know period, you can always find frequency. Using t as 1 over f. Period is t, that's what we're solving for. We know the frequency is 0.1 hertz. 1 over 0.1 is, should get 10 seconds. So these buildings, they're designed to absorb some energy, and so it sways back and forth, not by a lot, not like you'd be frightened to be in it, but it sways back and forth 1 complete time every 10 seconds. It takes 10 seconds to do this. That's what period means. 6. What is the period of a water wave if 4 complete waves pass a fixed point in 10 seconds? Alright, I want to point out something that can be very confusing here. And it's if you do 10 divided by 4 or 4 divided by 10. One of those will give you frequency. One of those will give you period. I'm going to set up both of them, and then we'll see if we can figure out which is which. So, as mentioned, 4 waves in 10 seconds. And then the other way setup would be 10 seconds in 4 waves. Now, one of these gives you period, the other gives you frequency. If you do the wrong one, then you answered the wrong question. Like you will have gotten this wrong. I like doing this. What is frequency? Frequency is, by definition, waves per second. That's what it means. Frequency is waves per second. Well, that means that this is frequency. Is that what I asked for? No, I said period. So let's not do that. Let's do seconds per wave. That would give us the period. The amount of seconds it takes for each wave to go by. 10 over 4 gives you 2.5. 2.5 is the answer. Number 7. A motor is used to produce 4 waves each second in a spring. Calculate the period and frequency. Alright, produced by the motor. So, 4 waves each second. If you've been watching for this long, waves per second, that sounds like frequency. So half this problem's done. Frequency is 4 waves per second, which another way we can write that is 4 hertz. Cool, halfway done. And like I said before, if you know frequency, you can always find period. Period is 1 over frequency. Equals 1 over 4 hertz. 1 over 4 is 0.25 seconds. There we go. Awesome. So the key there is understanding that waves each second, waves per second, that means frequency. Alright, what's the period of a sound wave having frequency of 340 hertz? This feels repetitive by now. Good. If you know frequency, you can always find period. 1 divided by 340. I should have done that ahead of time in my calculator, but I didn't. I got 0.0029. Now, I'm hoping that number sticks out at you as being like very small, like 0.0029 seconds. That's not a lot of time at all. But that actually makes perfect sense. 340 hertz means this happens 340 times per second. It must be happening very quickly, right? There can't be that much time passing. And this is not a lot of time, so that actually makes perfect sense. Question 9. A boy pushes his sister on a swing. What is the frequency of oscillation? So this is just a fancy word that means goes back and forth. What is the frequency of going back and forth of his sister on the swing if the boy counts 90 swings in 300 seconds? All right, I want frequency. Now, we're talking about swings, not waves, but it's the same idea. Frequency is waves per second, or swings per second. Let's just do that then. Frequency is swings per second. We've got 90 swings in 300 seconds. Throwing that in a calculator gets you, oh man, 0.3? I think 0.3. I'm going to pause this while I double check it. I was right, it's 0.3 hertz, right? 0.3 times per second. A duck floating in a pond oscillates, again, just means goes back and forth, up and down 5 times in 10 seconds. Determine the frequency. Again, frequency is waves per second. This happens 5 times in 10 seconds. So it's the number of times per second. So I'm going to do 5. I'm just going to fill 5 times per second. 5 times in 10 seconds is 0.5 hertz. 5 divided by 10. And that's it. So notice, and I really want to make a point out of this. You get most of this right if you remember frequency is waves per second, and that period is 1 over f. Those two things, if you can do that, you're mostly there. Last up, if the frequency of a periodic wave is doubled, what would happen to the period of the wave? Hopefully the phrasing sounds familiar. If this doubles, that halves, and all of those things. We did problems like that. And our process was we find an equation that connects period and frequency. And for each thing, we plug in, remember, it was like a 2 if it doubles, a 1 if it stays the same, a 3 if it triples, a 4 if it quadruples, a half if it halves, and so on. Alright, we said the frequency doubles. So I'm going to replace f with a 2, right? Because it becomes twice as big. So you get 1 over 2. That's it, right? Which means that the period is half. It's always a good idea to think about your answer. If something happens twice as frequently, twice as often, then it must take half the time for it to happen. That way, it happens twice as often. Alright, today we did, there's actually a whole lot going on, but to quickly recap here. We did mechanical waves, or we started mechanical waves, which is just transferring energy without transferring mass. Medium is what it travels through. We spent a while on the difference between transverse and longitudinal. Remember, transverse are the ones that look like this. They have a perpendicular motion, meaning that if the wave is traveling across, the particles vibrate up and down, which is what creates an up and down wave. Longitudinal means if the wave is traveling across or horizontally, the particles vibrate horizontally. And you end up with sort of just like a different pattern here of like compressions, expansions, compressions, expansions, and so on. Now we did period and frequency. If I had to boil this down to 2 simple things to remember, frequency is waves per second, and it's connected to period using this equation. T is 1 over f. That's it for this video. Thanks for hanging in there. I know it was a long one, but